Hi, thanks for joining again. So, this is the first of three videos that I'm recording about how to compile massive or any size, but even very large regular expressions by using a data structure called an adaptive radix tree. Now, um, this video we're going to talk about like why would you want to do that? The second video I'm going to talk about how to walk or traverse the adaptive radix tree data structure in order to produce an intermediate representation of the tree. An intermediate representation of the regular expression that you're producing, a logical representation, so to speak. And then the third video will talk about how you can translate that logical representation of the regular expression into an actual pattern string, how you can serialize it so that you can use that pattern string in a real regex engine. So in this video, we're going to talk about why you would want to do this. So another way of asking this is, well, what are the properties of the regular expressions, the regex patterns that we want to compile? So one of the properties is that you don't have to type it. Okay. why would you want to make a regex pattern where you don't have to type it out? Well, some of them are really long, and having to type it out takes time at the keyboard that you don't want to spend. So you don't want to have to type it out. There are other situations where it's not just laziness. You don't want to do that. There are legitimately situations where you need to produce regex patterns of a particular size at a certain pace that you couldn't possibly hope to do it with your keyboard, no matter how fast of a typer you are. Even if you hired people to help you, like you wouldn't be able to do it. You need some kind of automated solution. So that's one thing. Number two, we'll say you want the pattern to have a compressed size. So why would that be? Why would you want your pattern to have a compressed size? Well, some programming environments have a very strict character limit. Okay, there are just various restrictions in some programming environments that require you to be very succinct. Okay, and sometimes the simplest way of making a regex pattern can be very long, and there are techniques that you can use to shorten it. So that's one thing. Compressed size. Okay, so these are the two main properties of the types of regex patterns that are bringing us to this desire to compile them. So I'm going to explain one way that we can. I'm going to explain an example of a simple pattern that first, just for the purpose of juxtaposing, okay, the correct solution. One that would be really simple. Okay, so an entry level pattern. Let's say you have a list of words. Let's say these are names. Okay, so we have a list of names here. Now, the way that many people write regex patterns, especially when they're first learning, is they're like, well, I need to match any of these. And so you might write a pattern that looks like this, where you're just concatenating each of the words with this pipe character. Okay. And that's cool. Okay, that works. And realistically, with this specific example, it's so simple that it doesn't really matter, what engine you use this in, it's fine. But there are some downsides. So let's talk about the downsides. First of all, there are some characters that are repeated in this, aren't there? In the first two characters of these words, we have some characters that are repeated, some shared prefix aspect of this, right? So that's one thing that gives this the size that it does. There are other downsides to this. Okay, if you think about an algorithm, there to match these words, actually to solve the regular expression, there's multiple different techniques like backtracking and simulating finite state machines. But each of them could be impacted by the fact that imagine you have a word by this, okay? Imagine you have a word that seems like it could be in here, okay, but like it's not. So let's say, um, what's another T word? How about tipsy? Okay. So if you search for this word, you're going to start here. Is there a T? There is a T. Okay. So go to the next one. Is there an I? There is an I. Okay. Is there a P? No, there's not a P. Okay. Well, let's move on to the next option. And here we start back at the beginning again. Okay. Is there a T? Yeah, there's a T. Is there an I? There is an I. Okay. Is there an M? No, there's not an M. Okay, so go back to the beginning and start comparing again. Is there a T? Okay, and you see the problem. We're matching the T and the I again and again, and it's like, well, that's not really necessary, is it? Okay, so there's this like redundant effort, this repeated effort where we're matching something that's clearly there, and basically we don't want that. Even though this is a really simple example, a lot of times with regex patterns, simple things like that can matter because regex patterns can be scheduled to run many, many, many times in different places, servers, users' devices, and things like that. So little performance optimizations can matter. This is a simplistic example, but so one way that we can get rid of this inefficiency is to write a pattern that uses grouping, alternation, and concatenation, which are some of the core operators in regex, that it uses them effectively to avoid repeating these prefixes, okay? So we know, so I'm going to write a more efficient pattern than the one that we have here on line 10. We know that in any case we can match a T. So let's just put a T. And then we're going to enter a group. This is called a non-capturing group, but it could be a capturing group, whatever. But you need in fact, we'll do a non-capturing group because we're not capturing anything for this. This is just a matching exercise. So the question mark and the colon mean that it's a non-capturing group. And so in here, the second letter of each option is either an I or an O. Okay, so I'm just going to separate these for now. In fact, let's write this vertically, and then we'll go like this, okay? And then we'll kind of reduce it into a simpler pattern. So there's an I and there's an O. If you match an I, what's the next letter? Well, it's going to be an A, an M, or an N, and then an A. Okay, if it's an O, you're going to match an M, or you're going to match two Ds, okay? So we can use grouping and alternation constructs to avoid matching these shared prefixes over and over again. And here's how you might do that, okay? So you might say T, we're going to start a group, okay? And the first option in this group is going to start with an I, and the second option is going to start with an O. And so what comes after the I in the first option? Well, we need another group, okay? And in here, we could have an A, or we could have an M, or we could have an N and an A, okay? What about O? Well, we need another group here. We're going to have an O followed by either an M or a D and a D, okay? So even though this uses, actually, in this specific example, because it's pretty trivial, it uses more characters technically on line 21 than on up here. Um, in reality, when you have a lot of strings and you're doing this, you can save yourself a lot of space. But the real thing is that it's going to save you time in solving the pattern too, because if you look at this, it's not just space compressed. There's only one T in here. You're gonna match the T or you're not. If you have a word that doesn't start with a T and you try to match it like this, then that's it. You're done already. Or if you match the T, then you move on and you never have to worry about matching it again. You see, so it doesn't matter if it's a backtracking engine or if it's an automata engine. It's better to do it this way because it uses the grouping constructs effectively to kind of factor out these prefixes. Okay, so this is the kind of properties of a pattern that we want to compile. In the next video, I'm going to discuss how you can use the radix tree that I made, the adaptive radix tree, to compile such patterns from massive sets of strings. So I'll see you in the next video.